Okay, good morning, everyone. Let's continue in our course, Introduction to AI. And today we will go into games, into more complicated type of problems, and we will see how we can solve and play games. So, a quick recap. So, up to this point in our algorithms and in formalizations that we covered, we assumed that there is one agent, one player, one entity that is making changes in the environment, and we were trying to find like the best action that this agent, this entity can perform. Like we distinguished deterministic environment in case that we had, for example, search like A star and so on, or you have seen that in like with if we have stochastic events, so if the environment is stochastic, we have to like perform or use different algorithms, or we can learn the best plan. We can learn the best actions to be played, right? So this was basically up to this this moment in our course. And what is important to know is that the stochastic events, and if we have an agent in a non-deterministic environment, we assume that we know what is the probability of the outcomes of these stochastic events. So if I want to model something, some problem as a non-deterministic problem, I assume that I know what is the probability, for example, that my action will fail. And if you recall to our like very first courses and lectures, we assumed that we know the environment, right? Like we are learning and developing algorithms and problem-solving methods, assuming that we know what is the problem. We don't have to explore and learn first, like, what is the problem that we want to solve. Like, we assume that we know that. So we know that if our robot can fail, for example, when moving forward, we know that this probability of failure is, for example, 5% or 10%, right? So this is this was our assumption. So in today's lecture and next week, we will assume that, okay, the agent that is making the actions is not the only one in the environment. And we will have another agent that is making their changes, their actions in the environment. And they are making the changes such that they want to complete their own plan, their own goal, right? So this is the theory of games, because we assume that every agent, everyone that is actively acting in the environment, is trying to accomplish their own goal. And this is different to assuming that the environment is changing somehow stochastically, right? Like assume that we are playing chess, right? So, or you are playing chess with some opponent, and the opponent is trying to win the game for themselves, right? So like it's not true that you would know that that the opponent always plays this move in this particular situation, because they are trying to find the best move so that they can win, right? So so we will have like this situation where we have multiple agents, and each agent is trying to find the best action for that agent. Now the question would be, like, what is the optimal plan if we have this setting? And like what we will cover in these two lectures on games is a part of field that is called game theory. And game theory is really broad theory, and like very. Like if I have to like simplify it to one short definition, it's really about reasoning about possible actions and trying to find the best actions for each agent, assuming that all the other agents are reasoning about their plans, right? So this is what game theory is about. Game theory is really like I'm trying to find my best actions, assuming that I'm in an environment with all the other agents, and they are trying to do the same, and I'm trying to assume, okay, so if I'm going to act in this way, what are they going to do, and so on and so on. And this is really, really, really broad scientific field, and you can encounter game theory and study game theory from very different perspectives. Like game theory originally started as a sort of economic or mathematical science. However, like in, let's say, most or past 20 years, most of the game theoretic results were mostly computer theoretical or algorithmic. So what that means is that trying to solve the game, trying to find optimal strategies for some particular class of games are very, very interesting computational problems. And did you guys already have some form of theoretical informatics? And do you know what P hard or P classes NP hard is? NP hard. Does anyone know what NP hard means in terms of computational complexity? No one? Okay, so basically in theoretical computer science, you can categorize algorithms and problems into different categories, how complicated they are, right? And you can have like polynomial time algorithms for solving some problems, or exponential time algorithms for solving some problems, and so on and so on. And solving games is actually one specific, or some type of games, is actually some specific class of complexity problems, because it's very specific, very unique, and it's not easy, but it's not, for example, that complicated that some other classes of games. So from this perspective, like solving games was very interesting also for theoretical computer scientists. So like in this course, since it's again, like I repeat it on multiple courses, but we are in introduction to AI, right? So like we cannot really spend like much time on any particular topic. And for game theory, we are really going to talk and cover like the most basic games. And there are many, many other classes of games, other types of problems. I would say the most famous and most useful game theoretic problem that is applied every day are auctions. So whenever you search on Google, which ads you see is determined by auction, and how to act optimally in an auction is solving a game theoretic problem. So we will really only talk about game theory a little bit, but if you will be interested, there is a master course, computational game theory, there is even PhD course, and there are other courses, for example, on other universities. So like there is really a lot to study about game theory, and it's like the implications of game theory can be very interesting, especially I would say with the current rise of LLM agents. It can be very interesting, like how this, like the whole field of game theory can be useful, because like LLM agents are again rational agents that are doing something, and interaction of these rational agents is described by game theory. So we shall see whether like there will be some spike in interest in game theory. Okay, so this is like what's game theory, and now we have to answer one question, like why we are talking about game theory in an AI course at all, right? Like I described that the problems that we are going to study today are part of game theory, but what does this have to do with AI? And if you recall, on the very first lecture, William mentioned like some advancements in AI that were measured by playing games well, right? And there were many, I would say, very famous results where computer program beat some human like grandmaster or master in that particular game, be it chess, be it Go, or some other games. And as a part of measuring progress of AI, like games were, let's say, there with AI and with computer science from the very beginning. And if you know name John von Neumann, who is one of the grandfathers of modern computer science and economics, like he was very interested in games, in poker, in bluffing, and what does it mean mathematically. And one of the main theorems of game theory that are used and that like impacted algorithms and how to solve games is von Neumann min-max theorem. That, for example, is explained and covered in the master course. So, like from really 1950s, where computer science and AI was established, like the problem of knowing how to solve games was already there. So it was always part of AI. It was always part of computer science. And as I mentioned, like these games are really a good like measure and benchmark for determining like how good we are with the algorithms, because they are popular, right? Like when you design a new algorithm for playing chess or Go and so on, like it's very easy to explain other people that yes, I have this awesome algorithm and it can beat human masters in this game that you all already know, and like people rather know like these games like where multiple players can play because they are more fun compared to, for example, Sokoban that I was mentioning that was quite unfamiliar to you when we were discussing the planning. So like the single agent problem are usually less popular than games. So that's why like the games are really good benchmark, and usually the like state space that we need to explore is still like very challenging, very huge, because the number of combinations again grows exponentially. So like solving large games, for example Go or other even larger games than Go, can be very challenging. So since I mentioned like we have only 2 lectures on games, we will need to restrict only on some small topic from game theory, and we will cover the simplest game or class of games there is. And what are these like simplest class of games? We are going to focus on 2-player games. So in general, in games you can have n players, right? Like if you have for example auction, like you really are competing with all the people that have placed their ads into, for example, Google ad system. So you can have really multiple players, or in eBay or in some other auction, like you have multiple buyers, right? So in general, you can have many players, but today, like we will restrict the problems only to 2 players, and we will focus only on games that are so-called strictly competitive or zero-sum. Again, this is the simplest class of problems where if one player wins, the other player has to lose, and vice versa. If the second player loses, the first player loses, then the second player is winning. Or there can be a draw, right? But there cannot be a situation where there is a sort of win-win, right? Like either one has to win and other loses, or vice versa. Again, like this is the easiest class because it's kind of clear what each player wants to achieve. But in general, like in game theory, you don't have to have zero-sum game. You can have a general sum game where you may be looking for some win-win situation, but this can be more complicated because it's not really clear then like which outcome is better, right? Like this win-win situation is better than some other win-win situation, and so on. So like it can get a little more complicated. So that's why we are sticking with zero-sum games. And finally, we'll have perfect information about the game. So you will be able to solve with the algorithms that we'll cover games like chess, Go, or tic-tac-toe, or all the other games, or possibly, and we will touch on this towards the end of the lecture today. Like we can allow for some stochastic events in the game. Like this is possible. So, for example, backgammon is perfect information, two-player zero-sum, but there are stochastic events. So this is possible, but like we will not cover games like poker, because in poker, of course, like you don't know what the opponent has in their hands. If you do, then it wouldn't be a very fun game. So this is the restriction. And again, like solving imperfect information games is a lot more complicated than solving perfect information games. And again, like the imperfect information games are covered extensively in the master course, Computational Game Theory. So, how did we split like the topic of games into 2 lectures? So today you will learn about how to find like the optimal solution, the optimal strategy in a sort of classical way, search-based algorithms, where we will basically generalize what we learn about search algorithms, and we will like introduce algorithms that are variants of branch and bound algorithms. Branch and bound algorithms are class of algorithms where you are trying to prune some areas of the search space that you don't want to explore. And we'll see like what that means in games. Moreover, like since games have been solved and played with these type of algorithms for 50 years, many very useful heuristics have been developed for these games and for these algorithms, and they can be still useful beyond games. So this is why we are going to cover this. And then the next week, William will cover how to use bandits. So the fact that you learned in the reinforcement learning part of this course, so how to incorporate that into games. Like what does it mean if we take the bandits algorithm, if we take, for example, UCT, and what that means for games, right? So this is what we will cover next week. And like ultimately, like nowadays, modern game playing algorithms, even for this class of games, are based on Monte Carlo sampling, Monte Carlo tree search, and algorithms like UCB and UCT and so on. So this is like the like current version of the algorithms. But as I mentioned, like these algorithms that we will cover today, you can see it really as an example how to use search algorithms and how to apply it beyond games, because like the ideas are still valid. Okay, any questions so far? Okay, so let's write it down like formally, and we had the definition of games and their formal representation as extensive form games in lecture 2, but to recap and to write it all down, we can represent the sequential games with perfect information and two-player games visually as a game tree, and formally using several finite sets. So we have a set of players, and as I mentioned, like we are going to restrict ourselves to two-player games. So our set of players is going to be 2 players, 1 or 2, or since we are in a zero-sum setting or strictly competitive setting, we will have just one like utility value or one reward that one player is going to maximize and the other player is going to minimize that value, because like they are competing about the reward. One wants to maximize the reward and the other one wants to minimize it, because they are like the game is strictly competitive. So that's why very often like you will see that the players are also called as max and min. Right? So we assume that first player is now maximizing and the second player is minimizing the utility. Then we will have a finite set of histories, and these histories are basically decision points in the game, or basically states of the game. So if you recall, when we discussed like how we can formalize the state of a game, for example, for a chess, we arrived at conclusion that like remembering the set of history is a valid representation because we don't have to like remember all positions if by any chance like there wasn't like threefold repetition and so on. So even formally for all extensive form games, the state is formalized as a set of history of actions from the initial position to the current position. So this is these are the states. Actions like for each initial or for each state where there is some legal move, like we have a set of available actions that can lead us to another decision point, another history, or we can reach the terminal state of the game where the game ends, and these are basically the leaves of the game tree. And for each leaf of the game tree, we have some utility value that assigns some value for this leaf from some interval. And we will use like very simple utility values. Like in chess, you can have utility values like 1, 0, and -1. 1 means that white won, -1 means that black won, and 0 means that it's a draw or stalemate, and so on. So these are this is the formal definition. So again, like I want to emphasize the main difference where up to this point, like we had usually reward on the transitions, on the actions, right? And in games, you have like the reward, or it's called utility here, only at the very end, right? So like this is quite common. For example, in chess, like you don't get points for the fact that, for example, you capture some piece from your opponent. You get the actual reward and only when you win the game, so at the very end. So this is why the formal representation also like follows this rules. Okay, so this is the formal representation, and like technically, like if you, for example, open some book or on game theory, very often like you see that in games, basically every player is trying to maximize their own reward. Like this is a common assumption on the rationality of agents that are playing the game. And in here, what it means is that like we assume that the game is zero-sum. So we can have like two utility functions, one for player 1, which can be like this one, and the second utility function can be minus the first utility function. So what that means is that if we like take the sum of these two utility values in every leaf, the sum will be 0, hence the name zero-sum games. And if the utility value or utility function of the second player is the negative of the utility function of the first player, then minimizing the utility of the player 1 is actually the same thing as maximizing the utility value of player 2. So we are not like doing something else just because like we are in a simpler setting. We are basically still maximizing the utility for both players. It's just that utility function of the player 2 is very, very specific. It's minus utility function of player 1, right? So that's why like it's sufficient to have just one value. Then it's much simpler. All right. Any questions? Okay, so let's dive into the games and let's see how we can solve them. So, we will have this simple game that we will use for demonstrating number of algorithms and how can we solve the games. Sorry, no, only 2. Okay, I got carried away. So we have only 2. Okay, so we have this very, very simple game with 2 players. Every player has just one action to choose, and then there is the end of the game. Okay, so first, like this is the start of the game. This is the root of the game tree. We start here, and first to move is the player 1, or maximizing player, and the maximizing player can choose from 3 different actions. They can move left, in the middle, or right, and then like the second player finds out which action the first player played, and they can choose in each situation from like 2 different actions, right? So in here, I marked it x1, y1, x2, y2, x3, y3. Okay. So we have this very, very simple game. And in the leaves, like we have utility values, and the first player is trying to maximize the outcome, the value, and the second player is trying to minimize that. So how can we solve it, right? Like, what does it mean? So in like when we had just one player, one agent was acting in the environment, then it was easy. Basically, we would like to find, you know, like the highest reward, highest utility, right? So it's like we would like to get here. However, in games, like we have here the second player. So if the first player plays right, like the second player doesn't have to play x3. On the contrary, the second player wants to play y3, because from these 2 outcomes, y3 is better for second player, because the second player is minimizing the utility. So never ever, if we assume that the player 2 is rational, which we assume, so never will happen that in this case, in this state, that the mean player will play x3, right? The mean player here will always prefer this action. What about here, right? So what if the first player plays in the middle, then the second player will play, sorry? Sorry? Yeah, to -1 or y2, right? So like in this situation, the second player will play this action, and in this situation, again, like the minimizing player will choose the action that minimizes the value. So what can the first player do? Like, what is the best action for the first player? Yes, the first player is maximizing the minimal outcome, and if we look at what are the minimal outcomes, we have 2, -1, 3, and a maximum out of that is 3. Right? And what did we do, you know, like in this sort of reasoning on the board? So we assumed that, you know, all the other players, and in this case, that the minimizing player is going to play rationally, so it's going to minimize the outcomes, and we are acting assuming that the other players are rational. So we assume that the minimizing player is going to choose these y actions, and under this assumption, the best action for the maximizing player is to choose L, because we'll get the highest outcome. So this is like the reasoning on this very simple example, and we can generalize it, right? Like we can basically go beyond just these two levels, and we can generalize it in such a way that whenever we are in some decision node, we are going to select such an action in that decision node that maximizes, or it's optimal for the player that is acting in that node. In here, we have chosen the action y1 because it's optimal in this node for minimizing player that is acting here. From these two outcomes, 3 is better for the player 2. In here, -1 is better for player 2. In here, y3 is better for player 2. And now we know what are the sort of values here. Let's use yellow. Because in here, I know that like we will get 3. I know that. In here, I will get -1. In here, I will get 2. And from these 3 values, the best action for player that acts in here, in this node, is to choose maximum, is to choose 3. And we can like do this for every node, every state in the game tree, and in this way we can basically solve the whole game, right? So we can propagate upwards these values, and we can compute this optimal value and optimal actions for all states. So formally, like if like we repeat this algorithm that we have just described on the board, if we write it down formally for any state, we get to an algorithm that is called minimax, or it's simply backward induction, where like recursively we can have a depth first search type of algorithm where the algorithm is trying to assess the value for each node, and we can start with like we are going to search in a depth first manner, so we are going to down in that game tree, and if we encounter a leaf, then of course the value of the leaf is the value of the node, so we can like propagate upwards the value that is the utility of that leaf. And if h, the current state, is the decision node, depending on which player plays in that decision node, we can either choose to maximize the outcome if it's player 1, so this is the case, or we minimize the outcome if it's player 2, right? So depending on whether player 1 is acting in that node or player 2 is acting in that node, we'll choose differently. And like we can do that, as I mentioned, for every state, and at the end, like we will get to an optimal play, optimal strategy for both players, and we will get to a value that the players will achieve for playing that game optimally, and this value is called value of the game, right? So like this term, value of the game, is actually like terminus technicus, because it means that if we have the optimal strategy for the whole game, this is like how much the agents, the players, will get utility, right? So this is the sort of value of the game, and the game like is considered solved if we know like this value. So from this perspective, for example, chess is not really like fully solved because we don't know that value. Like we have awesome algorithms that can play chess on a superhuman level. Like nowadays, it's very hard to beat a computer that you have. I wouldn't say in a cell phone, because this is true for some time, but maybe even like beating a computer in a watch can be very challenging. But it's not like there is no perfect strategy. Like we don't know the perfect strategy for chess, so it's not clear whether like white, for example, has a perfect sequence of actions where they can always win, or whether they can guarantee a draw, right? So like the chess is not really solved. Checkers, on the other hand, is solved. So for checkers, there is an optimal sequence of actions, and if I recall correctly, Yeah, I don't recall. I think it's draw, but I'm not completely sure. So take it with a grain of salt. But I know that it's solved, right? So it took non-trivial computational effort, but there is an optimal strategy for checkers. So for chess, it's still fun for humans to play. They cannot play against computers because like computers are too good. So it's basically impossible to beat modern computers in chess. But people can still play it because there is no like ultimately beating strategy. Like if they were, then like you will have to play some other versions of chess where this doesn't hold. Okay, so this is the value of the game. Like if we can find really like the ultimate strategy for the game, then this is called the value of the game. Okay, any questions? So we have our first algorithm for solving games, and of course, like in many cases so far, the first algorithm, yeah, it works, but it doesn't really scale, right? So like we will spend the rest of the lecture trying to scale it up and improve it so that we can solve larger games. So let's think and let's look how the algorithms traverses through the game tree and what do we know at each stage of the algorithm. So when we start, in exploring the game tree in a depth-first search manner, we start with the root node, and of course, like we first evaluate the first child, and then the first child, and so on and so on. So we are going to down the game tree, and then we'll like propagate upwards the values as we computed them. So I will erase these values for now, and let's sort of backtrack what the algorithm is doing here. So let's assume that we start with playing the first action and then playing the first action in this node L, and since this is a leaf node, the algorithm propagates backwards value 4. This is the utility value of that leaf, and like in that moment when the algorithms finds out that okay, I'm here, I'm in the node of the minimizing player, and my first value that I have explored and found by playing one action, x1, is 4. So what can we conclude in this moment? Like I have just received value 4. What the algorithm can conclude about possible value here without looking anywhere else? What is necessarily true if I find out that after one action here, x1, I will get value 4? What I can say about this value? Exactly, it's at most 4. So after receiving 4, I know that the true value that I don't know would be less or equal than 4. Because I'm minimizing, and in here I can have value that is lower. But if there is a value that is higher, for example 10, minimizing player will never choose that action with value 10. Right? So the value in here is at most 4. Make sense? Okay. So I will evaluate second action. I will get value 3. And then I can update this that the value is at most 3 because I have found better solution, better from the perspective of the minimizing player. And I have no other actions to evaluate, so I know that it's not less than equal 3, but it's actually exactly 3, and I can write the 3 here and propagate it here, right? Okay, now I can continue with a second action medium. What's like how do we translate this for this root node for the maximizing player? So before we call this second action, what is true for the value in the root node? At least 3, exactly, right? Because in here we are maximizing. So we have found some solution, some sequence of actions that guarantee the first player to be able to achieve at least value of 3. We already have that. We don't know whether it's the optimal solution, but we already found it, right? So we can be only better after exploring the other actions. So let's call the second action in the middle, and I will evaluate first action x2, and since it's value 2, I know that the value of this node would be at most 2. And now, what can I see? I have here some condition, and I have here some condition. Exactly. So after exploring and finding this value of 2, I know that the value of this node would be at most 2, because this is minimizing player, right? So if here it's -1, it will be even less. If there is a 1 million here, it will be still 2. It's at most 2. Okay, but above the minimizing player, I have maximizing player, and the maximizing player has already found some action, some solution with a value at least 3. So no matter what I have here, and again, you know, as we had in CSP and other type of search algorithms, assume that I have here 10 power to 12 nodes, not just this one simple -1 value, but no matter what is the solution and value of the subtree, this will never be part of the solution. Even if there is 1 million, if there is a best strategy, best outcome for the player 1, this will never be reached, right? Because the minimizing player, if there is 1 million, the minimizing player will choose 2. So I don't really have to explore this branch. And after finding out that this value is at most 2, I can stop exploring and searching in this node, and I can backtrack to the root node. And this is like one step of the branch and bound type of algorithm that works in a game, right? So again, given the fact that we know at this point that no matter what we have in here, like this will never be part of the optimal solution, we can stop searching, return back, and then continue with other actions. So this algorithm that I have just described is called alpha-beta algorithm, and like we'll see on the slides how it is again written down formally. But the idea is this one. Before we go into formal description, any questions to this? Mm-hmm. Okay, mm-hmm. Because as I mentioned, when we get to 2 and we return back, we know that the value for this node, for basically this subtree, is at most 2, right? Yeah. So we know that the players can get like the value here at most 2, but the first player here is maximizing, and the first player here can guarantee for them value at least 3, right? So we can have here value 2 or 1 or 0 or basically anything that is less than 2, and no matter what value here would be, the first player, like comparing value 3 from this subtree and value here, that can be at most 2, will always prefer to go here. So we don't really need to know precisely what is the value. We just know that it's less than 2, or at most 2, right? So basically, what we sacrifice is to know exactly what is the value of this subtree, because we don't need that. We just know that this is not part of the optimal solution. And that's why we don't have to search for the exact value of this tree, because we know that it doesn't change the optimal solution for the whole tree, for the whole game. So that's why we can stop here. And like formally, how do we know that? Like you will see in the formal description of the algorithm. But the intuition, is it clear now? Okay. Any other questions? Okay, so these steps are basically like description of what I have just told you. So formally, we call like this type of search algorithm or pruning algorithm alpha beta pruning. Why alpha beta? Well, because we have two bounds on the value. We have lower bound and upper bound. Lower bound is alpha, upper bound is beta. So hence alpha beta algorithm or alpha beta pruning. And for basically all the nodes, like we have these bounds, and these bounds represent interval where we know that like we are going to search for the value of that particular subtree. So we start with minus infinity plus infinity, because at the beginning we don't know anything, right? And minus infinity is alpha, plus infinity is beta. And then like we go and we like search as previously. So again, like we start with, like we propagate these values down. We have minus infinity plus infinity. And then after exploring x1, we know that the value is at most 4. So we change our interval to minus infinity 4. Then we change it to minus infinity 3 after exploring x1. And then we propagate that 3 upwards. And you can see that in here, for the minimizing player, we are updating the upper bound beta, like we were in this part of the algorithm, because like minimizing player is trying to minimize the value. So if I find value 4, I know that the outcome is at most 4. So I'm modifying the upper bound, the beta, right? But when I propagated the value up and I'm in the maximizing player node, I'm modifying the lower bound, alpha, because I have found a solution with value 3, and I can be only better, right? So I have alpha equals to 3, and this is basically this part, right? So I search in a recursive way, and I update the lower bound as a maximum of my current lower bound and the value that I have computed. And now I propagate these bounds further, and I am already propagating the lower bound to the subsequent search. And after propagating or getting the value 2 from child node x2, my interval is 3, 2. And this is why now I know I can stop searching, because my interval is empty. My lower bound is higher than my upper bound. And this is my condition in alpha beta pruning. And whenever beta or upper bound is lower than the lower bound, then I can stop searching. And that's how I know that I can stop and not explore this part of the algorithm. sorry, of the search tree. Right, and then like I will go back. I have still value of 3. I'm exploring here again with values 3 plus infinity. After exploring the first child, I will get 3 and 7. After exploring second child, I have 3 and 2. And again, I can prune out. If there were some other actions, I don't have to search through them anymore, and I will propagate upwards the value 2. Any questions? Okay, so this is alpha beta pruning. Like the alpha beta pruning is I would say a very common and famous algorithm that was really used in for example, chess playing programs for a very, very long time. And it can be really, really effective because it guarantees you optimality, so you don't lose optimal solution, but can still like significantly prune out the search space, so we can really speed up the algorithms. And like you can solve much larger games using alpha beta pruning. So this is what we discussed, and now we are going to look into variants of this algorithm and how can we use it, and how can we like use it in a, I would say, very different way, right? So you will like the chance that you will implement alpha beta algorithm in your future work, no matter what that work is almost zero. But like try to see what are or how the subsequent algorithms that we are going to cover use the idea that I have, you know, this type of search with 2 bounds, and I'm trying to prune the space. And how can I use this type of algorithm to speed up the search without like substantially modifying, you know, the whole idea? So we are going to use it as a sort of hammer, and we are going to just like tweak some parameters, and the whole algorithm will behave slightly differently. And I think this is like one of the very interesting things that you can learn, that you can have multiple algorithms and multiple tools and multiple hammers, and it's very like you can use them in a very different way. So try to see this as an example how this hammer that is alpha beta pruning can be used to get very different algorithms. So before we dive into specifics, one clarification that you can encounter when you will be reading through some other literature, and this is algorithm called Negamax. And basically in many of the standard games like chess, Go, tic-tac-toe, really like most common games that you can encounter from our class of games, players are alternating in their moves. So, you know, player 1 is at the move, then player 2, then player 1, then player 2. So it's really strictly alternating. Like for our definition, we don't require that. So you can have technically player 1 making 7 moves, and then player 2 is making a move. So like this is valid extensive form game, but most of the common games, players are actually alternating. So to write down the algorithm more compactly, you can basically use this formulation where you like don't have to distinguish whether we are in a node of player 1 or player 2, and the algorithm always maximizes the outcome, but the algorithm changes the sign of the utility values and also changes the ordering of the bounds. So basically, Negamax is doing exactly the same thing as Minimax plus alpha beta pruning. It's just that it's more compact, and I would say also more confusing. So for educational purposes, like try to disregard this and try to use like the full version that I have on the slides, because specifically for more complicated algorithms like Negascout, it can be quite complicated to actually remember, okay, now I need to switch it and multiply by -1 and then turn around the alpha for beta and so on, right? So this is really just for you to know, because if you, for example, Google Negascout pseudocode, very often you will find the Negascout pseudocode in written in this manner, where you have multiplication by -1. But in my opinion, it's just way too confusing. So that's why this clarification that it's basically the same thing, but it's much easier to understand if I have that one if, depending on if I'm in player 1 node or player 2 node. Okay, so now let's dive into how can we play with alpha beta and what can we do. So you can see that when I traced the steps of the algorithm, I started with the bounds -infinity plus infinity, because at the beginning, let's say we don't know anything about the game, so this is definitely valid, right? I'm not doing anything illegal or suboptimal if I'm choosing the initial bounds -infinity plus infinity. However, what happens if I have some estimation that the value of the game can be, let's say, 10? I can have some heuristic function. I can train, for example, neural network, and my neural network will tell me that, okay, the value of this game from this starting point is 10. Because it's learned in this way, and it generalizes to unseen position, so it estimates that the value is 10. Okay, so can I use it? So can I, for example, say that, okay, if I think that the value is 10, what happens if I run the search with different bounds? What happens if I, instead of using -infinity plus infinity, I will use the exactly same search algorithm? And the only thing I will change at the beginning is that I will not initialize the alpha beta with -infinity plus infinity. I will initialize it with 9 and 11. 9 would be my lower bound, 11 would be my upper bound. Okay, and I'm running the alpha beta pruning as we defined it. No other change. So what's going to happen? So the game tree is trying to, or is looking a little bit messy, but let's try to do it again step by step, and we'll find out what's going to happen. So I'm starting with the root node. Nothing changes in the root node. I'm exploring the first action L, then first action x1, and after x1, my upper bound is going to change to 4. Right, in the same way, because I'm choosing the minimum of 11 and 4, which is 4. So after exploring x1, my bounds would be 9, 4, and I'm pruning out y1. Right, and I'm propagating up value 4. In here, I will and in the root node, again, nothing changes. I have 9 and 11. In the second subtree, I will evaluate x2. Again, I'm changing the bounds and the upper bound, and I will have 9 and 2. And again, I'm pruning y2. And in here, if I do the same thing, I will have 9 and 7, and I'm again pruning out the y3. So if I have the algorithm implemented correctly, and I'm going to propagate up the maximum value of these 3 incomplete search of the subtrees, the value that I will compute would be the value 7, right? Because it's a maximum of the values that these searches returned. Because I have 4 here, 2 here, and 7 here. Maximum of those values is 7. So what happened? So two things happened. First, 7 is not the correct solution of the game. We know that. We know that the value is 3, right? So we have computed incorrect solution. But we have pruned out quite a lot of nodes. Right? Like we have pruned out y3, y2, and y1, y2, and y3. So there are advantages and disadvantages. So one advantage is that, like, if we restrict and make the this interval alpha beta smaller, we can prune out more nodes, so the search is more aggressive, much faster. Right? So that's benefit. The disadvantage is that the value that we have computed is incorrect. But it's not completely incorrect. Like, it's incorrect for a reason, right? So it's not random. And if you look how these values affected the search, we can see that the values basically stopped the exploration in some of the minimizing player, some of the nodes of the minimizing player. And we know that because that value 7 is lower than the lower bound. So we know that somewhere in the search tree, in the game tree, it happened that due to this fact, like the minimizing nodes of the minimizing player were not explored properly. And it's true, right? Like, we haven't explored properly this node, we haven't properly explored this node, and we missed the correct solution here. We missed the 3. So thanks to the fact that, like, we know that the value that we have computed using these estimations is lower to these estimations, we know that the algorithm made some suboptimal pruning in a minimizing node. So we also know that the true value can be only lower than 7. So yes, it's fact that, like, we have not computed correct solution, but if we now, like, rerun the search with -∞7, we are guaranteed to find optimal solution, which is 3, right, in this case. So the fact, like, what would happen, you know, like, if we get the value that is within the intervals? Then we'll get, you know, the happy path and happy scenario where we computed the correct value, and we have pruned out the most or many nodes, right? So this is, you know, like the happy case. But if we don't have the happy case, we still get some useful information that we can use for subsequent search. And this is, like, what is very interesting, that the algorithm is the same. Like, we haven't changed the algorithm. We just use it differently, right? And this is what I found very, very interesting. So we can have these modifications for alpha beta, and on the slides I basically summarize what I have just told you using the board. So we can have positive impact, we can evaluate fewer nodes, but we can miss the optimal solution. So this is, like, going through the example, and the value that we computed is value 7, and we can, like, find out, or we can conclude that the value 7 indicates that the true value of the game would be lower than 7, because some of the nodes of the minimizing player were not properly explored, some actions were not visited, and we need to revisit those actions to actually get to correct optimal solution. Right? So this is the observation. So we can, and of course, like, if the value would be higher than 11, then we know the true value is higher, and we need to explore with different bounds, starting from that higher value. So we can then, like, generalize this idea and say, okay, so now I don't really have to use alpha beta as like using these standard intervals, like something to infinity or infinity to infinity, but I can use it with the smallest interval possible, just to get the estimates of the value. And what I can do is basically to have a search on top of the search with alpha beta pruning. And I can search for the right value, for example, by dividing the intervals. So I will guess the value. I will guess that it's 10, okay. So I will create a small interval, and I can go even smaller. I can create interval 10, 11. And like these small intervals are called null windows. And with these small intervals, I can prune very quickly, or many nodes can be pruned. So so I will search through the game tree very, very quickly, and I can get an estimate whether the value is actually higher or lower. And based on the fact that it's higher or lower, I will create another estimate. Okay, so I will get that it's 7, so I will run another search with, for example, value 4 and 5. And then 3 and 2, or 2 and 3, and then I will find a solution, right? So I can have like a search on top of a search. And really this was, like, again, prior to many other algorithms, this was, like, this idea was behind, like, one of the most successful search algorithms. And in 1996, like, they made a study of exactly, like, this type of usage of alpha beta algorithm. And practically speaking, like, these algorithms were a bit faster and a bit more useful than just plain alpha beta. Like, it depends on other factors, but this was this like usage of alpha beta in a sort of meta search was really used and really useful. So this is why I think it's very interesting to think about this in a sort of like different way, how you can use this hammer, this tool that you have, in a very creative way to get to even better algorithms. So this is like how can we like modify and use the whole algorithm just using the bounds, and we can also change the bounds dynamically during the algorithm. So how can we do that? So in order to do that, or in order to understand why should we do that, it's important to know like what is the impact of the order in which we explore the actions. And whenever like we have these examples on a board or on a slide, we assume that the actions are explored from left to right. Like this is some common thing that is assumed for ages, that we explore left, middle, right, always from the left to the right as we write. So this is the assumption. However, in the game where you're actually implementing alpha beta, like it really depends, and it's your choice, like which action is going to be explored first. And it can really matter. It can really matter whether the first action that the algorithm is exploring is the correct one, or the optimal one, or whether it's not. So consider these two game trees that are basically the same game, right? These are the same game that we have here, and the main difference is only in the ordering of the actions, where on the left you have basically the game as we had it so far, and on the right just two actions, middle and left, are switched. Right? So you can implement this game in either way, and we know that the left is the correct action for the maximizing player to choose. Right? Like we computed it, the value is 3, and the left is the optimal action. So previously we had it like correctly, and the maximizing player was first exploring the optimal action. And we have shown that for alpha beta we are able to prune out this action y2. Right? Like this was like the node that that alpha beta pruning can prune out. However, if you retrace alpha beta pruning for the game formalized on the right. So the alpha beta algorithm will like follow the ordering as it is on the right figure. The algorithm will not prune anything, right? Because in the first node you will get the value of minus first 2, then minus 1. So the value of here would be minus 1. So you propagate here minus 1, and then like you will never encounter any sort of empty interval that would cause the pruning of the alpha beta pruning. So the one difference, just the ordering, can cause the difference whether the algorithm will actually prune some nodes or not. And in general, like in the worst case, alpha beta algorithm or alpha beta pruning will not prune anything. So if you have completely incorrect or opposite ordering of the actions, then alpha beta will not prune anything. If you have optimal ordering, so if you really sort the actions from like the optimal one to the like worst one, then you can prune quite a lot, and basically you can like search game trees with more or with twice as deep as without it, right? So so this is really like the difference when you're implementing game playing algorithm. Like if you can search further, your algorithm most likely would be better, right? So the difference is really huge. So of course, like we don't know the optimal ordering, because like if we knew it, then like we don't have to search for anything. We will just like play the first action. So this is more dependence on having a good heuristic, and the heuristic will give you the ordering. So like the better heuristic we have, the better ordering we have, the more effective also the alpha beta pruning is. And there is one other algorithm that heavily uses this idea of having a good heuristic that will like most likely correctly provide me with the best action first. And this is called Scout or principal variation search. So in this algorithm, we will really assume that, okay, I have some heuristic, some ordering of the actions, and I assume that my first action is actually the correct one, and all the other actions are less good and may not, like most likely don't contain the optimal solution. And how can we use that, use this assumption in a search? So we can modify these intervals as we have seen here, and if we assume, you know, like we still like strive to have optimal algorithm that will give us optimal solution. So we will assume that, okay, like if we assume that the first action is really the optimal one, we want to compute the correct value for that particular action. That means like whenever we are exploring the first action of some node, we are not going to like modify or change our alpha beta interval in any way. So for first actions in every decision node, I'm going to like use the search as if it were alpha beta. I'm not changing anything. However, when I explored the first action in every node, I'm assuming that all the other actions are worse. So I'm just going to prove myself and prove so that I have guarantees that I have optimal solution. I'm just going to prove that all the other actions are actually worse. And how the algorithm does that, it's that the algorithm then generates or creates a smaller interval. So artificially, I'm going to change and modify the interval inside the search so that the proof that the second action, third action, fourth action, and so on is actually worse is done as quickly as possible, so that I can prune out as many nodes as possible, and I will only check the value that is the outcome. I don't need exact value exact values from these subsequent actions. I just need a proof and validation that my first action was correct, right? So, this is the idea behind Negascout, or it's called also principal variation search. So again, like the first action is evaluated with standard interval of bounds alpha and beta, and for the second and all the other actions in every node, I'm trying to minimize the interval as much as possible and call that search with so-called null window. Like the interval is called window. If it's as small as possible, it's called null window. And if I get the result from that null window search, like two things can happen. Either like we'll get a value that is like worse for the player that is making the decision in that node, and then I have my proof that okay, like this action is really worse. Like similarly, to this, I know that the value, is smaller than the interval, so I know that the true value lies within this interval. I don't need exact value. I have a proof that okay, it's worse, and I can stop like evaluating this action. Or like the value would be actually better for that player, and then I have to search again. I have to repeat the search for that particular action, because otherwise I could have missed the optimal solution. So this is the second case, that if the returned value indicates that like the true value of that subtree is actually better, the algorithm will rerun the search again with wider interval to compute the optimal solution. Okay, so you can see that it really is dependent on having a good heuristic. So if you don't have a good heuristic, then very often you will have to rerun these searches to explore some actions multiple times. But if you have the good heuristic, very often like you will search fully only the first action, and then all the subsequent searches can be much faster because they are executed with very small intervals, and hence like these searches can prune out many nodes. So how it is implemented and like how do we create these small intervals? So for some like history nodes, for some state, again, like if it's if it's a leaf, then we just return the utility value of that leaf. And if it's a decision node of player 1, then for the first action, we just evaluate and like use the depth first search as before, so nothing changes. And like after the first steps, and we update the lower bounds and so on and so on. For all the subsequent searches, we set a new artificial upper bound for the, like if we are in a maximizing player, we are setting artificial upper bound beta prime to alpha plus 1. So for first search, we have alpha beta as an interval. After first search, we may update alpha. But for the second search, we have alpha plus 1. Right? And if from that second search we get value that is higher than lower bound, we need to do the search again. But if it's not, then we go further. Okay, so this is Negascout, or principal variation search, and for the second player, like this is very similar. The main difference here is that for the second player, like we are updating the lower bound, right? So basically for each player we are artificially modifying that bound that is not being updated using like regular updates or regular search, right? For maximizing player, like when we explore different options, we are modifying lower bound. So our artificial, like making the interval artificially smaller, for that we modify the upper bound because like the lower bound is basically the value that we have found that is the best so far. So we modify this for the second search here to 3, 4, right? For the minimizing player, we do it differently. So if we explore this action first, then for the second call, we will have 3, 4 again, because like 4 is something that we fix, and 3 is something that will be artificially set. So this is Negascout, and Negascout again using good heuristic can be faster. So usually 10 to 20% depending on the heuristic, depending on the game, but it can be faster, and like it was used in I would say chess playing programs before the Monte Carlo tree search algorithms that you will learn next week about. An example to demonstrate like how this can help in a slightly more complicated tree, because for like showing that Negascout can really prune more nodes, we need slightly more like larger trees than this tree. So we have an example on the slides where like we can assume that after calling, evaluating this subtree, we get a value of 4. So for this subsequent call for evaluation of the right subtree, we modify, or the algorithm modifies the interval to 4 and 5. So 5 is the artificial bound that the algorithm sets. For alpha beta, that would be 4 plus infinity, but for Negascout, it's 4, 5. And when the algorithm like goes through the search and the tree, then like in this maximizing node, the algorithm will like find the value 7 and update the lower bound here of this node to 7. But thanks to the fact that we have set the upper bound artificially to 5, this B is going to be like not explored. So we will have a pruning here. And this is really just because we have set the beta artificially to 5. Like for alpha beta, in this situation, we will have intervals 4 plus infinity, and we will just update 4 to 7. We will have 7 plus infinity, and nothing happens, and we explore action B. But for Negascout, we will prune this out, and we will not explore the action B in this node. So this is the difference. Okay. So any questions to alpha, beta, Negascout, and these algorithms? So if not, then let's sort of conclude with some heuristics and observation and how these algorithms are actually like used, and what are the tricks and complications when you actually want to use them for game playing. Because the algorithms that we have described, and like as we described them, we were talking about game solving. And if you recall that we have defined the value of the game as if we solve the game, so we have the optimal strategy for the whole game from the beginning to the end of the game. Like this is what it means that we have solved the game. We have the value of the game. But in reality, like we cannot really solve chess, because we don't have that much compute power. Maybe in a few years we'll be able to do so, but right now we just cannot. So what we can do is that we can play the game, and we can like find an algorithm that actually plays the game without the ability of solving the whole game. And like the chess is like one example that I use, but even Go or other games can be even larger than chess. And for all of that, like it's really impossible to store and to go through all the possibilities, even without all the pruning that we can have. So what we can do, and what the algorithms actually do, is that instead of using utility function in a game tree, we can use heuristic evaluation function. and we can create artificial trees and artificial leaves somewhere in the middle of the game. And what this basically means is that you will allow the search, for example, alpha beta, to search, for example, for 10 moves. And then instead of taking the utility value, because like after 10 moves in chess, you most likely don't end up in a terminal position. So you cannot take utility value. You need to take some other evaluation. And that other evaluation is some heuristic evaluation, estimating how good this position is or can be. Right? And this is usually what's being done when we have game-playing algorithm. Right? So like game-playing chess algorithm doesn't solve or compute the chess till the very end. It performs several moves, say 10, 20, maybe 50, right? But it's not till the necessarily end of the game. And therefore, like we need to have some values that are propagated up the tree, and these values are heuristic evaluations. So, for example, you can have like neural network nowadays that you can train to predict you like how good this position is, and you can use those values as the evaluation of the position. Of course, like creating and coming up or training a good heuristic evaluation is much more complicated for games than it was, for example, for single-player problems. Again, because like it's a game, so it's more complicated, and somehow in that heuristic function, you need to like encode the possibilities of the other player, so what the other player can do. So in chess, like usual heuristic is like whether you have more pieces or more valuable pieces than your opponent. But if your opponent is going to give you a checkmate, it doesn't matter that you have a queen or you are a queen up, right? So it's some heuristic, but it can be more complicated to come up with like very good heuristic. So it's challenging, and given the fact that it's challenging and it's been used for many years, there are, let's say, common problems whenever you are required to do sort of depth-limited search, right? And this is not only true for games, but also for other cases, again, where you can allow only to spend some time on doing the search, and then you need to use some evaluation. So, for example, like in chess and in games, like this can be quite well explained. So, let's assume that we are allowed to search for 10 steps, 10 moves, right? And after move 10, or we are under the attack, and the only way how to avoid the attack is to sacrifice the queen. And if we sacrifice the queen, then maybe we can win, right? So like this is really like the right move to do. However, if like we can, for the algorithm, postpone sacrificing the queen and sacrifice, for example, 2 pawns that have lesser value than the queen, then the outcome of the heuristic value function, if we don't have it correctly, can be like better, higher for us. So we will sacrifice, those 2 pawns. Then like we'll make move and we'll find out, okay, we need to sacrifice more pawns, and so on and so on. So we will sort of postpone the decision that decreases our heuristic evaluation, even though this is a necessary step to do in order to play optimally, right? So. This is the sort of famous problem of the horizon, and again, like this problem is well studied in games. However, whenever you will artificially create some horizon for any problem that you will encounter, try to recall this lecture and try to look into the literature on really game playing and chess solving, because there are many heuristics and tricks. How can you avoid this problem of horizon? And you can adapt that to your situation. right? Because, for example, in chess, like they find out that, okay, this is really a problem, especially if the pieces are being exchanged. So, for example, if you have fixed horizon of 10, it doesn't really count if the pieces are being exchanged. So in that case, you search actually longer, right? So for more moves. And really, like given the history and time spent on these algorithms for games, like there are many tricks that you can use for other domains as well. So this is one of it. Another good heuristic is basically using a cache. Sorry, using a cache. So you can like reach the same position using multiple different move orderings. So you can cache the values that you have already computed, and in games this is called transposition tables. So you can store the value. However, it's also good to store that value, for example, with the bounds with which you computed it, or with the depth to which you have explored from that particular state, and so on and so on. So again, like if you need to use cache in some more complicated problem, in some more complicated search, look for transposition tables in games, and again, you will find a lot of tricks from the 50+ years of research in this area. So these were like the most famous heuristics, and we are slowly out of time. So let me just conclude with games with chance. So we can quite easily expand and modify our definition of two-player games by introducing a third player called nature or chance, where we will not specify that that player really maximizes or minimizing the utility, but that player behaves and acts according to some well-known distribution. So, for example, if we have a game with chance where we roll a dice, then each action of that dice happens with probability 1/6, right? So we can easily specify that, and then, for example, in minimax, nothing really changes, because the value that can be propagated up is basically the expected value of all the children multiplied by their probabilities. So like minimax algorithm can be very naturally extended to games with stochastic events. However, for alpha-beta pruning, this can be a bit more challenging. And we are not going to cover deliberately alpha-beta with chance nodes over in the lecture, nor in the labs. This is your task. Try to think about this and try to think whether you know how to generalize alpha-beta pruning to games with chance, right? You should be able to look at this game and answer these questions. And if you are able to do that, you understand alpha-beta correctly. So try to take this as a homework, like for yourself, to check whether you really know and understand alpha-beta and how, like, what does it mean to change alpha-beta for games with chance, right? Really, this is sort of test for you. Like, if you are able to answer that and reason about this, then you understand this topic. If not, and you are unable to figure this out, write me an email. Okay? And that's basically it. We are out of time. Just like for you to know, I think William mentioned Deep Blue as one of the milestones of AI, where Garry Kasparov was defeated by IBM Deep Blue algorithm, and the Deep Blue algorithm actually used Negascout as like the main algorithm. So like what we covered really was like part of the history of AI, and of course like there were other things, but like from the algorithmic perspective, they used Negascout. So that's it. Thank you very much, and we'll see each other next time.